It's time, folks, to start our review into some of those topics we haven't seen in a while, specifically vectors. So this is an IB question. It's actually from the 2009 Paper 1 exam. And we're going to go through it, and I'm going to use this as an opportunity to review some of the ideas of vectors that you might not have thought about in a long time. So let's get into it. So we have three position vectors, OP, OQ, and OR. Now let's remember what position vectors really mean. This means that the starting point of this vector is O, and the ending point is P. Now I have drawn point O, which represents the origin on this diagram. And so even though the way things have been written here, this is not a two-dimensional problem, I'm going to make a sketch that I think will help review some of the ideas behind this that might make clear why we're allowed to answer questions the way we can answer them using vector properties. So for example, I'm just going to put P, Q, and R in the coordinate plane here. And I'm going to draw some of these vectors. So vector OP is a vector that goes from point O, that's here at the origin, to point P. And the direction matters when we draw this out. Vector OP is going to go from here, point O, to point P. We're going to draw the arrowhead there so that we see what the direction is. Let's start answering this question. So this has vector PQ. So that means we are interested in finding this second vector, PQ, which starts at, again, right at P and ends at Q. So let's draw that vector. PQ looks like this, and again, the arrow is going from P to Q. This question is asking us to find this vector. Now, one other thing that I'll point out in order to get there is that vector OQ is one of the given bits of information. So vector OQ looks like this, again, with the arrow drawn that way. The way that we can find vector PQ is by looking at this diagram and remembering how we add vectors graphically. You'll notice that the vector OP is kind of our starting point. At the tip of vector OP, we have vector PQ. And then we have a vector that is drawn from the tail of the first vector, OP, to the tip of the second vector, PQ. In other words, this is a graphical way of representing the vector sum OP plus PQ equals OQ, just because of the way we've drawn that. So to find PQ then, what we need to do, we can just subtract vector OP from both sides, and we get that PQ is going to be vector OQ minus vector OP. And now we can just use the components of these vectors to actually find what that equals. So vector OQ, we have 3, -1, and 2. And from that, we're going to subtract vector OP. That is 3 minus 4, -1 minus -3, and 2 minus 1. And so if we do that, we end up with a vector -1, 2, and 1. So that is our answer for PQ. We can also find vector PR. Now, in a similar way, we can draw these vectors out. Vector OP plus vector PR is going to be equal to vector OR. This is the same arrangement as what I drew for OP, PQ, and OQ. So this means that to find PR, we again are just going to subtract. So vector OR minus OP. We can do the same subtraction that we just did. OR is 6, -1, and 5. And OP is still 4, -3, and 1. And that gives us the vector 2, 2, 4. Okay, next thing. We are to show that cosine of RPQ is 1/2. Normally, in problems involving vectors where you're asked something about the cosine, this normally means just kind of looking at the topic, you might be looking at the dot product. So RPQ, if we look at what's happening in this diagram that we've drawn, now again, it's not necessarily that accurate, but it doesn't matter. RPQ is the angle between, and let me erase some of these now. RPQ is the angle, since P is in the middle, that's going to be the vertex. So we're looking at RPQ, angle of what we're looking for here. And so that's going to be the angle between vectors PQ and vector PR. So this angle right here is that angle RPQ. So what we want to do then is figure out PQ and PR, because we can use the dot product to relate those vectors to the angle between them. So you might remember that with the dot product, if we have PQ dot PR, what that means is that we take the magnitude of PQ, we multiply by the magnitude of PR, and then we multiply by the cosine of the angle between them. And let's label that as cosine of angle RPQ. We can find PQ and PR because we just found PQ and PR. So let's start by finding what PQ dot PR is equal to. The way we find a dot product is we take the components of the two vectors, we multiply the individual components together, and then we add the results. So again, PQ is this vector that we found up in the part A. -1, 2, and 1 is PQ. The dot product of that with PR, which is 2, 2, 4, means we're going to take -1 times 2 plus 2 times 2, it's the middle two components, and then plus 1 times 4, which is the product of the final two components. We add those together, -2 plus 4 plus 4, we end up with 6 as that dot product. We also want to find the magnitude of PQ. The way we find magnitudes of vectors is using the Pythagorean theorem, and this works in 2 dimensions and 3 dimensions. So to do this, I'm going to take the square root, and I'm going to take each of the components of PQ and square them. So we have -1 squared plus 2 squared plus 1 squared. And it's a good idea to keep them in parentheses so you don't make any sign mistakes. Putting all of that together, we end up with the square root of 6. The magnitude of PR, we do the exact same way. That's going to be the square root of 2 squared plus 2 squared plus 4 squared. And that ends up being the square root of 24. So now we can take all of this information, we can take this relationship, which is the definition of our dot product, and rearrange it to be written in terms of cosine. So cosine of RPQ is going to be equal to the dot product, PQ times PR, divided by that product of magnitude. So PQ times the magnitude of PR. And we found all of these values already. So we have 6 in the numerator, and then in the denominator we have square root of 6 times square root of 24. And we can simplify that radical a little bit. Here's a 6. We can look in the denominator and see that we end up, if we multiply these over, the 6 times 24 is 144. So this is 6 over 12, which is cosine of RPQ being equal to 1/2. And that's what this question is asking us to actually prove. So we've finished this part. We're being asked to show that cosine of RPQ is 1/2. Second part, part C, it asks us to find sine of RPQ. So actually at this point, this problem stops being a vector problem and starts being a trigonometry problem, which is great for the purposes of our review. So if you know cosine, the question is, how do we find sine? One thing you might get from your formula booklet is this, this identity, and that identity is that sine squared theta plus cosine squared theta is always going to be equal to 1. So if we know that cosine of RPQ is equal to 1/2, we can use that fact to figure out what sine is going to be. So let's substitute that value in. So we have sine squared theta plus 1/2 squared is equal to 1, which then tells us that sine squared theta is going to be equal to 1 minus 1/4. So sine of theta is equal to the square root of 3/4. Now the only thing to be careful of here is I haven't really stated the relationship between angle RPQ and theta, so let's do that formally. Let's just say let theta equal of angle RPQ. So now we can get away with just writing that shorthand. Now the only thing, I'm going to put this plus or minus here because when we take the square root of both sides, we don't know if we're squaring a negative number or a positive number. So what we have to decide is whether the positive number or the negative number is relevant here. Which one actually matters for this particular problem? Because we are dealing with sine, and because we're dealing with vectors, and these angles, generally when we're dealing with vectors, those angles are almost always going to be between 0 and 180 degrees, or between 0 and pi radians. This is just a convention. We know as a result that we're just interested in the positive value, which means that the sine then of angle RPQ is therefore going to be, just simplifying this radical a little bit, square root of 3/2. There is one other way to obtain this that I know we went through when we did trigonometry, and that is you could draw a right triangle for this. So the way you could draw this right triangle is you could say that if the cosine of an angle is 1/2, then you know that this right here, here's our RPQ. Okay. The cosine is the adjacent over the hypotenuse, which means that the opposite side, therefore, has to be square root of 3. And since the sine of an angle is the opposite over the hypotenuse, the sine of angle RPQ would again be square root of 3/2. So you could do it that way as well. Either way is fine in this case. You still need to think about the sign, S-I-G-N, positive or negative of this, but in the case of vectors here, sine is going to be positive between 0 and 180 degrees, or 0 and pi. So here you're not going to get a negative sign, so you don't need to worry about that. The final thing is, going back to our question, find the area of triangle PQR, which we can kind of go back and look at the diagram we drew. So PQR is our triangle, and you might have either from the formula book or you might remember that we can find the area of a triangle by doing area is 1/2 AB sine of theta, where that theta is the angle between the two sides that you know the length of, so that A and that B. And we know that in this case, A is going to be the magnitude of PQ. So A is the magnitude of PQ, so we know that value from what we did up here. The magnitude of PQ is square root of 6. We know that B is PR, so that's the other side of the triangle surrounding angle RPQ. So B is the magnitude of PR, which we have figured out is 24. And we also know that theta, we also know what sine of theta is. So sine of theta is square root of 3 over 2. So we can just substitute in. This becomes 1/2 square root of 6 times the square root of 24 times square root of 3 over 2. And we can do some simplification on that. Lots of ways that we can do this. We have a 1/2 there, square root of 6 there. We can write square root of 24 as 2 square root of 6, and then we have square root of 3 times 1/2, and so we can have a little bit of work to simplify that. We have a 1/2 there, multiplying the 2. We have 6 times 6, giving us the square root of 36, which is 6, and then 6 times 1/2 then is 3, so this all simplifies to 3 square root of 3, and sure enough, that is in the order, in the form of what the question asks us to do, specifically give it in the form of a square root of 3.